As a climate scientist, my research focuses on developing the high-resolution projections that people need to incorporate into long-term planning on everything from water management to infrastructure design. Why do we need climate projections today, though? The way I think about it is this. Here in West Texas, we have a lot of very straight roads. They are so straight that you could be driving down them, like this highway from Lubbock to Plainview, Texas. You could be driving down them, staying safely not only in the road, but even in your own lane if you were navigating simply by the rear view mirror. Why is that? Because when the road is straight, then the past provides a reliable guide for the future. But what happens if you're coming up on Plainview here and you hit this giant curve in the road and you are navigating entirely by your rearview mirror? Let's just say you'll end up somewhere you didn't plan to be. And that is a metaphor for how human civilization has been planning over the last decades, centuries, and even millennia. We have had regional variations in climate, and some of those have had serious impacts on local societies and civilizations. But long-term, the average temperature of our planet over the course of human civilization has been about as stable as that of the human body until the last century. Today, our collective bus is already veering off the road. Our wheels are on the rumble strip, and that is why it is time to look ahead down the road so that we can all make it around this curve safely together. We know that wherever we live, we have hot and cold, wet and dry. And climate is the long-term average of these weather conditions over at least 20 to 30 years. Over the course of human civilization, again, the long-term average has been stable. But what happens if that average changes? We care about a changing climate because it is altering our average future conditions, and these are conditions that we use for the basis of planning and management. But that's not all. We also see that climate change is altering our variability. And as it alters our variability, it is exacerbating many of the climate and weather extremes that we already see today. We know that across the United States, we see hundreds of these events. Texas has had more than any other state since 1980, but every state has had weather and climate extremes that have caused at least $1 billion worth of damage. These happen naturally. It's as if we have a pair of weather dice, and we always have a chance of rolling a double six. A double six is the heat wave, the heavy rainfall event, the flood, the drought, the wildfire. If you live in Texas, we already have 3 sixes on our dice. But as climate changes, it's sneaking in, so to speak, decade after decade, and taking one and then another of these numbers and turning them into sixes, and even we start to see the occasional 7. And we say, how could this be happening? The answer is climate change. In terms of its impacts on extremes, we see that heat waves are becoming more frequent and more intense, and cold waves less frequent, although we do still have them. Wildfires are burning greater and greater area because it's hotter and drier when they occur. We also see that droughts are getting stronger and longer in many areas of the world, including Texas and the Southwest United States. Heavy precipitation is also getting more intense. Why? Well, warmer air holds more water vapor. And so when a storm comes along, then there's more water vapor for it to sweep up and dump on us. But during droughts, storms don't come along. That's the whole point of a drought. It's a high pressure system or ridge that sits over an area, directing storms away from the area. So the drought gets stronger and more prolonged, and all that water vapor gets evicted out of the area. We also see that tropical storms like hurricanes that get their energy from warm ocean water are getting bigger and stronger, and they have a lot more rainfall associated with them also. So how do we characterize this curve in the road? One way that we can do so is by looking at the past changes that we've already seen. And if we are looking out a few years into the future, up to a decade or so, then the recent changes that we've already experienced are probably still going to be the most reliable guide for that period of time. But again, I'm emphasizing the changes that we've seen, not the long-term average. If we want to look forward into the future, 20, 30, 40, 50 years or more though, that's where we want to start to look at climate scenarios. What are climate scenarios and why do we need them? They are what-if scenarios. What if human population, energy choices, emissions, and temperature changed in a certain way? We need these scenarios because we can't predict human behavior. We humans are the ones driving this change today. All of the warming we are seeing is human-caused and then some. Why? Because according to natural factors, we should be getting cooler right now, not warmer. In fact, it's a little bit like Schrodinger's cat. By looking at the consequences of a higher versus a lower scenario, we actually have some hope that we might be able to change those probabilities. So let me give you some examples. For example, here are the carbon emissions corresponding to a higher and a lower future scenario. One scenario, we continue to depend on fossil fuels. The other, we transition off fossil fuels to clean energy and decrease our energy use through efficiency as well. The way I characterize these two scenarios for the purposes of adaptation planning is like this. The lower scenario represents what we'll have to adapt to no matter what we do, even if we try our hardest. So a lower scenario is a very helpful bench line or base mark of what we have to prepare for. And if a certain system is not able to cope with that amount of change, that's where we have to understand that maybe everything that we're investing might be for naught. But on the other hand, that enormous difference between the two scenarios, that's what can be avoided by prompt action to reduce our carbon and other heat-trapping gas emissions now. And so quantifying the difference between a higher versus a lower future shows us the impetus for why we would want to mitigate, because there might be changes that are too large to adapt to. When it comes to the future, the bottom line is this: the greatest uncertainty is us. So, all right, we know that the future is uncertain due to our choices as humans. We know that we need to use multiple scenarios to capture both the baseline, what we'll have to adapt to no matter what, and also the higher scenarios that show what could be avoided through mitigation. But how do we actually connect this to impacts in the place that we are concerned about? The main tool we use to do that is climate models. Climate models divide the entire world, the atmosphere, the ocean, the land surface, the ice, up into smaller and smaller grid cells. And in each grid cell, using basic physics, they calculate the impact of increasing greenhouse gas emissions or other impacts on climate that can occur naturally on our temperature, our rainfall, and more. This is literally a simple diagram of some of the physics that goes into a climate model. And I don't show you this so that you can peer at the details here. I just show you this to illustrate how complex these models are. What they do, though, is fairly straightforward. They take the initial forcing, which can be natural or due to human activities like carbon dioxide emissions. They take the initial forcing and they look at how that kicks off a chain of feedbacks within the climate system that lead to an even greater warming. That's called climate sensitivity. Climate models, you may be surprised to learn, began a very long time ago. The very first climate model was calculated by hand before we had computers back in the 1890s by a Swedish chemist named Svante Arrhenius. Since then, though, they have evolved very quickly to become some of the most complex pieces of code on the planet. And this diagram from the National Climate Assessment from my chapter 4, which explains scenarios and models, shows how these models are constantly evolving. People often ask, well, I know there's a lot of different models, but can't you just tell me which is the right one? Unfortunately, the answer to that is no. I cannot tell you which one is the right one because there isn't a right one. What we know is that the multi-model ensemble, which means when you put all the models together, the multi-model ensemble is typically closer to reality than any given climate model. And that's not the fault of the climate model. You really have to think of a climate model as a separate planet Earth. It's the same distance from the sun, it gets the same amount of energy from the sun, it has the same layout of continents, but it has a different pattern of natural variability. So let me give you a concrete example so you can see what the output of a climate model looks like. And this is actually downscaled output, which we'll get to in a minute. Here we have annual maximum temperature at one location. This is a weather station in Wilmington, Delaware. The black line is the observed annual temperature from 1960 to 2010, and the colored lines are a bunch of different climate models. So you might say, wow, these climate models are all over the map. How am I supposed to know which one's the best one? Well, again, the point is here, there isn't a best one, but when you put them all together, you see that the long-term trend over climate timescales, and again, climate is the average of weather over at least 20 to 30 years, the long-term trend over climate timescales is nearly identical between the ensemble of climate models and the observations. What's the second thing we see? The second thing we see is that the range of variability is nearly identical between observations and the climate models. So that's why we want to use an ensemble, not to figure out what happened or what will happen on July 18, 2052, but to look at the long-term trend in both average temperatures and extremes over that time. That's what climate models can give us. That's why we should always use climate projections over climate timescales, 20 to 30 years. We should recognize there's no one perfect model. Using as many models as possible is usually the best way to go. And we have to realize that there's no scenario that's more accurate because scenarios are driven by human activities. So we have to look at the future as sort of an if-then. If we do this, then this is what is going to happen. And lastly, we have to recall that because we're conducting a truly unprecedented experiment with the only planet we have, there is always the chance of surprise. So it's better to be safe than sorry. What does climate model output look like? Well, for the United States, we see up at the top the observed trend in temperature over the last century. And then on the left-hand side, we see the projected change under a lower scenario. And on the right-hand side, we see the projected change under a higher scenario. This illustrates the impact of our choices. But global climate model output at the scale of the entire United States, it can tell us that there is a trend, it can tell us the direction of the trend, and it can even often tell us a little bit about the magnitude of the trend, especially in terms of average temperature and average rainfall. But often we need a lot more than that. We want highly granular, detailed information for the places that we are concerned about. So that's where downscaling comes in. What is downscaling? Well, you have the different global scenarios that go into the global model, and then it produces information at the scale of the global model, which is typically 100 to 100 miles per side, per grid cell. And then we can downscale it to either individual weather stations or to a fine scale grid. There are many different approaches to downscaling, which is best depends on your resources and on your needs. So for example, if you're looking at a watershed that's fairly large, so a gridded data set of downscale projections at 1/16th degree, for example, would give you adequate coverage and resolution over the watershed. And if the topography doesn't vary too much, then a gridded data set might be perfect. On the other hand, if you are looking at a watershed where the topography varies significantly over very small spatial scales, or maybe you already use specific weather stations or gauges that your model is built off of, in that case, individual weather station projections might be more useful. And these are just two pictures here contrasting the two different approaches. So whether you use a grid or weather station information, again, depends on what you're most used to using. There's also two different approaches to downscaling. You can do high-resolution regional climate model downscaling, which gives you a grid, or you can do empirical statistical downscaling, which will give you either a grid or weather station output, depending on what observations are used to downscale. Each of these approaches has their uses. Each of them has their benefits and drawbacks. So statistical models are computationally efficient. They can run lots of different global climate models, lots of different scenarios, and they automatically bias correct the global climate model output so it's ready to be used. Regional climate models, though, have all the dynamics in them at the high resolution. So they can simulate, for example, the effects of topography on climate at a much finer scale than the GCM. They can also generate output for a lot more variables. Statistical models typically just do temperature and precipitation. Some of them can do solar radiation and humidity, but regional climate models can do a whole suite of variables with different soil layers and different layers in the atmosphere as well. You can also use regional climate models where you don't have any observations, but statistical models are limited to where you do have observations because that's what's used to train the model. So if I were working in a region with few or no observations, Or if I needed a large suite of complex variables like cloudiness, soil moisture, solar radiation, wind, I would use a regional climate model. On the other hand, if I were working in a region that had observations and I wanted projections that actually matched the temporal and spatial scale of the observations that I was using, or if I wanted to make sure that I had lots of different global climate model inputs and multiple scenarios, then I would go for a statistical model. What does this look like? I want to just give you an example here. This is a map showing where we have downscaled weather stations in Ohio, as an example. These are all weather stations. And across the US, we've downscaled temperature projections to a lot of different weather stations. And this animation shows, I think, 200 of them across the US. And what we've done is we've calculated the temperature of the hottest day of the year moving forward into the future, starting in the 1950s and going through to the 2090s. You can see how the temperature of the hottest day of the year increases over time under the higher scenario. So this brings us to our third and last question. How do we know what we need? Well, the first place to start is not with me, it's with you. What impacts do you care about? Do you care about drought, about heavy precipitation, about water shortages? What do you care about? And then step number 2, how do they connect to climate? So start with what matters to you in terms of planning and management, and then say, well, how does that connect to climate or weather? And then step 3, we can say, all right, how are these things changing? In some cases, all you might need to know is the fact that they're changing in the direction of the trend, because whatever management options you have available to you are not going to change significantly if I told you that heavy precipitation is getting 2 times more frequent or 3 times more frequent. If you would do the same thing anyways, all you need to know is that it's getting more frequent. And this type of information can be provided by regional assessments and by national assessments like the U.S. National Climate Assessment. Other times, though, you need more information. You actually need to have quantitative information that tells you the range that you can expect. So for example, if you knew that heavy precipitation was going to increase somewhere between 3 to 5 times, and the 3 was at the lower end of the scenarios and the 5 was at the higher end of the scenarios, so you'd have to adapt to 3 no matter what. But if you wanted to be safe rather than sorry, you might want to adapt to 5 times. Then that's where quantitative information can help. If your response is going to differ depending on how much things are changing, that's where you need quantitative information. And in the guidebook, we have a lot of details, and in Sarah's presentation coming up next, there's a lot of details about how and where you can find that quantitative information if you need it. But again, a lot of times you might start off thinking you need it, but it turns out that your adaptation options are so limited or prescribed that all you need to know is how things are changing and in what direction, and that gives you the information that you need to act. The bottom line is this. The future is uncertain, but we do know enough to act now. Our collective wheels are already on the rumble strip. The curve is looming immediately ahead, and it's time to take our eyes off the rearview mirror, maybe just keep one eye on it, and the other eye ahead down the road, because our goal is the same. We need to plan for that curve in the road to ensure that we all make it around safely.